All right, let's talk about piecewise functions. So piecewise functions are important and they just break down a function into like other parts. So they are like little mini functions, I guess is one way that you could call it. And as always, when we do tutorials, I typically don't answer the questions unless I feel it is beneficial for you or the lesson or the tutorial. And we don't watch the videos on here when I'm recording this. I let you do that on your own. Okay, so let's talk about piecewise functions. Now, I also have a little mini lesson on my YouTube channel that breaks down piecewise functions and kind of shows you a couple different examples and stuff like that about it. So let's look at these, the warm up. We will talk about this. It labels the different type of functions and it says this one is exponential, the first one. Exponential increases like dramatically. So it just goes like straight up pretty much. Square root functions always look like this. Quadratic look like the U shape or something along those lines. Linear is a line like that. So those are just examples of 4 different types of functions. Okay. Again, now we've looked at the type. Here's one type. Here's the difference. It shows you the difference, quadratic versus exponential.
Let's build a new function that uses the left side of the quadratic function and the right side of the exponential function.
Interesting. Well, let's find out more. Aha, now this is called a piecewise function. As you heard me say, it's kind of like piecing things together. So as you can see, quadratic plus exponential is piecewise because there's like 2 different types of functions right here.
The new function is a piecewise function made up of pieces of 2 different functions.
Mm-hmm. Pretty interesting. All right. So for an example on this piecewise function, we have linear, cubic, and square root all kind of jumbled together. Typically in a piecewise function, when you see the lines, you'll probably see them in different colors just so you can understand that here's the different pieces of the function. Okay, so linear. Let's talk about linear. Basically, the form is y equals mx plus b. That's just the standard form to find the slope of the line and all that fun stuff. So let's listen to this.
Linear. A linear function is in the form y equals mx plus b, where m represents the slope and b represents the y-intercept. The graph of a linear function is always a straight line. It is always increasing or always decreasing. This is the graph of the parent linear function f of x equals x.
All right, so let's look at polynomial. Now, as you can see, polynomial functions, they go a couple different ways. So when they're even, they look a certain way. When they're odd, they look another different way. So it's just kind of different with polynomial functions too. As you can see, they have like a curve to them. So let's listen.
Polynomial. A polynomial function has terms with a variable raised to an exponent. The highest exponent shows the degree. When the polynomial has an even degree, the ends of the graph reach in the same direction. When the polynomial has an odd degree, the ends of the graph reach in opposite directions. These are the graphs of the parent quadratic function f of x equals x squared and the parent cubic function f of x equals x cubed.
All right, so let's take a look. Now that's why, as you can see, that here's the 2 different equations for the function x squared and x to the 3rd power or x cubed. Exponential, as you can see, there's a dramatic increase or a dramatic decrease depending on, let's see which one we're looking at. So let's listen to what it says about exponents.
Exponential. An exponential function is in the form y equals a times b raised to the power of x. When 0 is less than b less than 1, the function is always decreasing, quickly at first and then more slowly. When b is greater than 1, the function is always increasing, slowly at first and then more quickly. These are the graphs of the parent exponential functions f of x equals 1/2 raised to the power of x and f of x equals 2 raised to the power of x. Both functions have a horizontal asymptote at y equals 0.
Okay, so as you can see, they give us the example about the function is always increasing slowly, and as you can see, it slowly increases at first, and then it increases dramatically after that. So it starts off pretty slowly, and then it goes dramatically up, and then it just keeps increasing up, 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 and up. Okay, so now let's go to rational functions. And these, they're usually on like two different sides or two different quadrants of the graph, just like this. I'll play the audio so we can listen to what it says.
A rational function has a variable term or expression in the denominator. This is the graph of the parent rational function f of x equals 1 over x. Many rational functions have two parts. The graph is split because the denominator can't be 0. Function f has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0.
All right, as you can see, and they're in two different quadrants again, and how this is the equation like 1 over x like that. So this is kind of the function you would see for something like that. Radical. Now these are different. They're kind of like square root functions or cube root functions. So let's listen to what this has to say.
Radical. A radical function has a variable term or expression under the radical sign. These are the graphs of the parent square root function f of x equals the square root of x, and the parent cube root function f of x equals the cube root of x. We can't take the square root of a negative number, so square root functions have domain restrictions. We can take the cube root of a negative number, so cube root functions don't have domain restrictions.
Okay, so these are cube root and square root functions. So let's go. This is a piecewise function now, and it's three pieces of three different types of functions or equations all combined together. So piecewise function looks like this, and this is how it's represented. Here are the three different equations that correlate with the function. So we use these three, combine the whole graph together, and it looks something like this. So it's a function made up of multiple and non-overlapping pieces in which the relationship between the independent and dependent variables may be different within each piece. Okay, so here's how it looks. Here's just the different equations, and they're just highlighting the different pieces and the different parts of the equation so you can see what it looks like. Here's another example of a piecewise function. We'll let you kind of solve this one. These just show different examples. The first piecewise function has three different equations in it. The next one only has two. So again, these are just different pieces and different piecewise functions and what they are. So let's say it's a non-continuous function, a function that is defined for all real values and that when graphed has no gaps. So no gaps means that it's connected together. Okay. So this graph is discontinuous because it has a hole right there, the little mark. The domain of the function, it does not represent the value. So it's discontinued because it's not connected together. This one is discontinuous because, again, the two graphs are not connected, or the two lines are not connected together. They're just two segments. Again, this one is discontinuous because they're not connected. Okay, so another example of the questions, we'll let you answer those. Graphing them. So how do we graph a piecewise function? Well, you have to look at the different parts of the equation, and then you figure out where the points would lie on the graph and what quadrants. You mark the points down, and then you draw your line, connect your graphs, connect your pieces, all of that. So that's kind of how it would work. So let's look at this. Here we're putting in the pieces on the table. It's showing you step by step of each equation. Here's the line. So, okay, here's our line that we're drawing. So these are the different equations we have. Here's our points. We've plotted them on our graph. Here's what it looks like when we draw the line connecting everything, okay? Okay, so the questions, yeah, I'll let you do the questions on your own for this. Online graphing tool, if you need help with any of the questions on the tutorial, this one is the online graphing tool is always good. It shows you how to graph the functions, and you are able to plot your points on here, and it kind of shows you what to do. So it's pretty good. Oops, let me get back. Graphing with technology, again, this shows you online calculator and shows you how to graph the different pieces on the functions. Good tools for you when you're trying to figure these out. And if you're answering some of the questions, it makes it a little bit easier. So a radical piece, to enter the cube root function, select functions in the keypad. So that means that you're putting the functions in the keypad over here. And then the button for all the radical functions is miscellaneous. And you use the edit list to figure out how to color code it. And when you're plotting your points down on the graph. So some of those might come in handy when you're answering the questions. You might want to refer back to how to graph it over here. Analyzing key features. So this just shows different functions again as x approaches negative infinity. F of x will approach positive or negative infinity. And then sometimes it's vice versa, positive infinity to negative infinity, or positive infinity to positive infinity, meaning that the graphs are going to go on forever. That's the simple term. The graphs will go on forever. So here we have another piecewise function. This 3 different equations here, or 3 different functions here. We have 1, 2, and 3. As you can see, they're kind of separated. It's showing you the y-intercept, showing you the constant and how it's increasing, and it's showing you the range of our function. So this right here is how to determine like the range, how to determine the domain. Continuous means all values of x in the domain are represented. Where one piece of the function ends, the next piece starts. So the function f has no points of discontinuity. So that means basically the graph is connected together in simple terms. That means that it's not they're not like discontinued, they're not open, they're not scattered all over the place. All right, so here's just some more graphs, more examples of how to do it on our calculator or our graph, online graph. Make sure you go back to that. And we'll go back over here, the questions. I'll let you do these questions on your own though. Real world problems, piecewise functions, think of like a roller coaster car. That would probably be the best example for something like this. Height of a roller coaster car, it just shows you more examples. More of how to graph the functions and what to do. Kind of fun. Think if you can find another example of a piecewise function in everyday life. So as you can see, and if you can see why this would be a roller coaster car. So it starts up at the bottom, goes up, kind of levels off for a sec. You go down the hill or down the roller coaster, and then sometimes you go back up again, something like that. So a roller coaster car would be like an example of a piecewise function. Think of any other examples that you might have. I could think of one, sledding. So you're sledding down a hill. You have to start off like you're walking up the hill, you get to the top of the hill, put your sled down, and then you go down the hill, and then sometimes you go back up depending on how the hill is. So it could be something like that. All right, questions. Like I said, I'll let you do all these questions on your own today. Because a lot of this is just like do it yourself, play around with the graphs and the online calculator. So that's a lot of do it yourself stuff. Here's other types. So this is an absolute value function on the left. Step function is on the right. And as you can see, I'm sure you can guess why it looks like a step function because the function is, well, looks like step. So that would be why. Now let's see absolute value functions. A function defined by the absolute value of an algebraic expression, usually seen as piecewise with linear parts, meaning 2 functions are linear, they connect together in the middle somewhere and makes absolute value. So then there you have it. There's 2 different equations here. They're connected together, and that's what makes it the absolute value function. Okay, so these are just different examples, and I'll just kind of briefly touch on them like this. Okay, so that's just another example. I'll let you answer those questions again. Step functions, and as you probably guessed it again, they look like steps. So it kind of looks like a staircase. Here's the equations and the functions, and then here's how they are plotted on the graph. So a step function, a piecewise function is defined by constant linear segments. So we have line segments, basically, that look like a little mini staircase. See? There you have it. And this, again, will be like playing around with the graph. So I'll let you answer the questions on your own. Hopefully that clears it up a bit for you. And we'll just kind of go show you these. And I'll probably just play the audio on each of them real quick for you, just so we hear it once more.
Piecewise function. A piecewise function is made up of two or more pieces. Each piece of the domain relates x and y differently. The equation of a piecewise function shows an expression and a domain inequality for each piece. F of x equals negative 2x plus 1 for x less than 0, and 2 raised to the power of x for x greater than or equal to 0.
All right, let's play the audio on key features.
Key features. Here are some key features of piecewise function g. Y-intercept of 3 and x-intercepts of negative 3 and 1. Increasing over the interval negative infinity to 0 and the interval 1 to infinity. Decreasing over the interval 0 to 1. Domain and range of all real numbers. Not continuous. Point of discontinuity at x equals 0.
Okay, let's look at this. The point of discontinuity, a point that is not on the graph of the function, but where the function graphs jump, breaks, or has a hole. Let's listen to absolute value.
Absolute value functions. Absolute value functions are piecewise functions made up of two linear pieces, one decreasing and one increasing. We can rewrite the equation of a function in the form f of x equals mod of bx minus c as this piecewise function. F of x equals bx minus c for bx minus c greater than or equal to 0, and negative of bx minus c for bx minus c less than 0. Here are two equations that represent function h. H of x equals mod of x plus 2. H of x equals x plus 2 for x greater than or equal to negative 2, and negative x minus 2 for x less than negative 2.
All right, let's take a look at the last one, step functions. Play the audio for you real quick, and then we'll call it a day.
Step functions are piecewise functions made up of constant linear pieces. The graph of a step function is made up of horizontal line segments that look like steps. Like other piecewise functions, the equation of a step function includes an expression and a domain inequality for each piece. J of x equals 2 for x greater than or equal to negative 5 but less than 0, and negative 2 for x greater than or equal to 0 but less than 5.
All right. So there you have it. There's piecewise functions for you. Hopefully that cleared it up a little bit for you, and hope you enjoyed.